All right, this is lecture 6, still on chapter 3 on evaluating properties, second half of section on evaluating properties. So again, we're going to introduce property relations, and we're going to show you how to use the ones or find the ones that are relevant to engineering thermodynamics. So a repeat from previous lecture, once again, it is so that you need two independent variables, two independent intensive variables to fully determine the state of a system. So this to say you have to have a pair pressure, temperature, pressure specific volume, pressure specific heat, which we'll introduce here, maybe pressure internal energy, maybe internal energy and temperature, pairs like that. Okay, so how do we do this? Well, we saw last lecture that you do this using a PVT diagram. What's going on here? By using a PVT diagram. Now, the PVT diagrams which we described before was for water, and you had here two-phase water that was both ice and water. You had here two-phase water that was both liquid and vapor. Now, the point is that water is a system where when you freeze it, it expands. If you look at ice, the ice floats on top of the water. That also happens to bismuth. Bismuth actually floats on top of its liquid. Very few substances do that. These are the two only ones that I know about. Most of the cases, the solid is actually denser than the liquid, and so the solid has no buoyancy. The solid would fall to the bottom. Not so with ice. You notice that that is important here. The shape of this two-phase region where you have simultaneously solid and liquid, that shape is re-entrant vis-a-vis the vapor dome that you have here. So if you go from liquid to, well, this is a solid. If you go from solid to liquid, you will actually have a specific volume that decreases. Now, if we look at most substances, it looks like this, actually. So we have here the PVT diagram for a system that contracts on freezing. So here we have the vapor dome. And here we have, going from solid to liquid, we have the specific volume that decreases. Going from liquid to solid, the specific volume decreases. So this region of the phase diagram here, which is easier to see in this type of solids, is the equivalent for to the vapor dome, but for the solid to liquid transition. Another strange property of most of these gases, and liquids and solids, is that there is this critical point. And there is a region above the critical point where you're above the vapor dome. And so in this region, the fluid has supercritical behavior, which is a little bit strange. I illustrate that here in the case of carbon dioxide. So in the case of carbon dioxide, if we're here, we will have a liquid and a gas that we see quite clearly. As we approach the critical point, this separation line between liquid and gas, which is very clear here, becomes blurred, more blurred, more blurred, and in the supercritical fluid, it's completely gone. So this is the state of the liquid. Liquid gas, you don't know what it is. It's a mixture of both here, whereas this is clearly in the vapor dome where we are here. It does actually matter because we are going to use supercritical fluids. We will use supercritical water in steam turbines, and some of the refrigeration systems use supercritical carbon dioxide like what I showed here. All right, so to summarize what we have most of the time for water, oh, by the way, here is the supercritical point for water. It's 647 Kelvin, so it's about 400 centigrade, 380 centigrade, and it's 22 megapascal, 220 atmosphere. It's quite high, but some of the turbines and the power generating plants use that. So let's now review systematically when we go from left to right. At a given pressure below the critical point. So we're not going to work here for the moment. We're just going to work here. If you are here, you have the subcooled liquid, sometimes called compressed liquid. That is because you're at a temperature below the saturation temperature. The saturation line of saturation temperatures for a given specific volume is here. Temperature below that, you're going to be in the subcooled liquid region. At saturation, you're going to be having a saturated liquid. So it's a liquid that has a tendency to start boiling at the pressure at which you are, but isn't quite developing bubbles yet, because the pressure in the bubbles doesn't balance the pressure of the air above it. But it will. If you add a tiny little bit of heat to that, you will start the process of evaporation. So now the liquid will go into a two-phase system, a little bit of liquid and a little bit of vapor, or a lot of vapor when the X is high. And here you will transform your liquid to vapor with a new variable, which will be the quality of the steam, the X. So when you are at saturated vapor on this line, that means X is 1. On this line, X is 0. In between, X is somewhere between 0 and 1. That is when you're at the saturated vapor region. If you go above the saturated vapor region, you're going to end up in the superheated vapor, T above the saturated vapor, that is here. And this process is for all substances that we will use, typically water, steam, refrigerants, and air in principle, although for air, this point at atmospheric pressure would be at 77 Kelvin, or, well, air is a mixture. Nitrogen 77 Kelvin, oxygen is a little bit above that. I'll move on to a next topic, which is a new concept, that is enthalpy. So enthalpy, by definition, is the internal energy plus the product of P and V. Why do we do that? So the sum of the internal energy and the product of P and V is something that we will use in practice. It's not a fundamental unit. It's a practical unit, and it will be particularly practical when we will be working with open systems. I don't tell you why now yet. That will come in 2 chapters from now. And that has a new name. It is here in absolute numbers, so it's in joules or in BTU. That is to say, these are the extensive versions of it. It is a state property, and you can have it in intensive properties as well. So you can divide this by mass, and the volume by mass. Then you have the specific enthalpy per mass, the specific internal energy per mass, and specific volume per mass. This is in joules per kilo, BTU per pound. Or you can divide the whole thing by moles. H divided by N, U divided by N, V divided by N, and you end up with H bar in joules per kilomole, U also per kilomole, and P in V in volume, cubic meter per kilomole. All right. So in your tables, as we have seen before, we had rows for temperature, pressure, specific volumes, and internal energy, and enthalpy H. And then we had this mysterious thing that was called entropy. But the fact is that you can use H or U or V just as well as you can use P or T as the intensive variables that you want to use to characterize your system. Now, another thing in the tables is that there are reference states. When we go through a process between the state initial and the state final, we always calculate the differences between these state variables. So specific volume, internal energy, enthalpy, and entropy are state variables. So you just don't need to know how the process goes from initial to final. You just need to know the state, initial and final, and you can use these differences to calculate your properties. Well, if you use differences, it really doesn't matter where you set the 0. So the offset, a constant offset in the tables, if they're consistent between all the specific volumes, although we don't have an offset there, but all the internal energies and all the entropies, the enthalpies and all the entropies, you can set the 0 when you want. Well, the place where you set the 0 is called the reference state. So one can demonstrate that U is minimum actually at 0K, but that doesn't have to bear on how you're going to be using your tables. One does have to state that entropy is 0 at 0K. That is a principle of thermodynamics, but it is of no consequence to you. It's just a fact. So now, actually setting U at 0 Kelvin is not particularly practical because we're going to be using around room temperature or even at temperatures far above room temperature. So it is just as practical to define a reference state in an arbitrary way. And here in particular, we use for water, U is 0 by definition at T is 0.01 centigrade, saturated liquid, and pressure is so many bars. Now, for ammonia, we set it at a different spot. H is 0 at minus 40 degrees centigrade, P is 0.71 bar. Very often, the tables have been copyrighted. And the reference state is actually part of the copyright. If you make another table with a different reference state, it's just as practical, and you will avoid the copyright of the previous table. The problem with that is that many books have different reference states. So if you take a enthalpy that you read in the table of one book and you take an enthalpy that you read in the table in another book and make the difference, you may very well make a mistake. You have to look where the reference state is in the particular book that you're using. And in ours, sometimes in the psychrometric charts, the zeros, the reference states, are not at the same spot as where the tables have the reference state. So then you can't even go between the chart and the table. Always watch out in each table and each chart where the 0 is set. Now, the use of software, and I went into that in my oral lecture last time a little bit. I suggest that you read chapter 3.7 in the book on your own. It describes how to use software, and it describes two options for software, IT, which comes with the book, EES, which has built-in tables. That's great. But I do suggest that you practice your problems using just your tables. The problems on the exams, you're going to have to use the tables because I don't want you to have software available with possible exam problem solutions on it. So you might as well use the tables for your homework as well. On the other hand, if you want to use software, which is indeed faster, and if you want to do that on homework problems, go ahead and use it, as long as you know how to use the tables as well. All right, now we introduce a new concept, and that new concept is specific heat. So let's go back to the first principle. Delta U is Q minus W, or Q is delta U plus W. So this heat is in joules or in BTUs. The definition of the heat capacity of a system is how much heat it can absorb if you add a temperature delta T. So it's delta Q over dt. I had to write this with this silly delta because this is not an equation of state, whereas temperature is an intensive. But that is what the definition is of the heat capacity of your system. Now, of course, if you take the heat capacity and you halve the size of your system, you take a mass that's double the size of the previous one, you will have, that's half the size of the previous one, you'll have less heat capacity. So the heat capacity, which is this, per unit mass, is the specific heat per mass, by definition. So here we have joules, here we have joules per Kelvin, here we have joules per Kelvin per kilogram, as far as the units go. We can have the specific heat per mole, where instead of using the heat capacity and we divide by mass, we divide it by the number of moles, and that is C bar, that is the specific heat per mole, the mole of specific heat, joules per kilomole per Kelvin, or BTU per pound mole per Rankine. So the specific heat is going to tell us, in this particular case, if you have no work, how U changes if you don't do any work, and how U changes with temperature. Under other circumstances, it will tell us how the enthalpy changes. I'll get to that in a minute. So remember now that the number of independent intensive variables you need to fix a state completely uniquely is 2. Well, so you can use this U is a function of temperature and pressure, or temperature and specific volume. And you can arbitrarily replace these variables. So you can take U is U of T and H, or H is H of T and V, or T and U, and so on and so on. They can also be a function of the heat capacity. Since U is a function of heat capacity, it goes here. Since U is a function of pressure and temperature, so is the specific heat. So now, how we exactly define this derivative depends on what other parameter we keep constant. In other words, you can define your specific heat under constant pressure. That will do one thing, that's one partial derivative, or under constant volume, and that's another partial derivative. And these two are not the same. So let's do that generally. Generally, because U is a function of pressure and volume, the derivative of U with temperature will depend on whether you take that derivative under constant volume or that derivative under constant pressure. This is this volume-specific heat. This is the pressure-specific heat. Now, let's look a little bit at what we do. We do per kilogram. So we can delta Q per kilogram, which is U and PdV, but PdV is 0 because V is a constant. So delta Q per kilogram is delta U lowercase. That means that since by definition CV is du dt, it's du dt at constant V. I just took mass and put it in here to get to that. And per mole, I have that, right? It's the Q dt really, but dQ is du, and therefore it's du dt. It's a little bit more subtle if we do it under constant pressure, because it's still dQ dt, but dQ now is du plus pdV. Remember, it's actually du plus pdV plus vdP, but because it's under constant pressure, the vdP is 0. So you end up with du plus pdV, and if you recall the definition of dH a few graphs back, it's du plus pdV plus pdP, because H is U plus PV. So this is du plus pdV, since vdP at constant P is 0. du plus pdV is the same du plus pdV there. That means that dQ under constant pressure is actually dH. The heat under constant pressure is the enthalpy, not the internal energy. The heat under constant volume is the internal energy. The heat under constant pressure is the enthalpy. That's why we defined enthalpy. It's to make use of this relation. Well, then, if I take the derivative of Q over T at constant pressure, I end up with the derivative of the enthalpy with temperature at constant pressure, and that is what the specific heat is at constant pressure. Or per mole, C bar P is dH bar dt at constant pressure. It is very important to define whether you are under constant volume or constant pressure for your partial derivatives that result in specific heats that are quite different in general. In fact, the ratio of the specific heat under constant pressure to the specific heat under constant volume is called the specific heat ratio, K, and we will use K all the time. It's very practical matter. This now leads us to asymptotic behaviors for our materials, for our substances. So let's go back to the vapor dome, which we have here, and in a P versus V diagram, or in a T versus V diagram, temperature specific volume, pressure specific volume. My vapor dome is here. This is my saturated liquid. This is my saturated vapor. Remember, your isotherms were horizontals here, and then they climbed steeply here. Isotherms were horizontal here, they climbed steeply there. And here, your isotherms extend far out. And hot is this way, and diluted is that way. So if you go to a limit where you're very hot and very diluted, out here, you have what we call the ideal gas. The whole ideal gas situation will be the subject of the next lecture. On the other hand, if you go to a situation where you have a liquid or a solid, which is the same, you will see now that these pressure dependencies as function of specific volume are very, very vertical for all the different temperatures. In other words, you can apply a very large pressure to a liquid without changing its volume very much. A liquid is incompressible. By definition, the incompressible state is one where this bar is totally vertical. So let's now look at the behavior of the specific heat under constant pressure and constant volume at these two limiting states. Well, they are going to be very different. In general, so, the specific heat or the internal energy or the enthalpy are a function of both temperature and pressure or temperature and specific volume. But in the limit of very low and very high temperature, we're going to have specific cases. The limit that we're being concerned with now, the next one will be for the next class. The limit we're concerned with now is the limit where the pressure is below the saturation pressure and temperature, below the saturation temperature mostly, where these lines are extremely vertical. When they are extremely vertical, the internal energy and the enthalpy to a lesser extent become independent on pressure, so that the specific heat at constant pressure is only a function of temperature, and the specific heat at constant volume is actually also only a function of temperature. Ideal gas we'll get to later. So, in fact, I can plot here the specific heat for various substances as function of temperature, and these lines are for various pressures. And this really holds for most substances. Just the temperatures and the pressures at which it happens depends on the substance. So now you can see that these specific heats at the lowest temperatures all tend to come together. That is going to be the limiting behavior for the incompressible fluid. This is the range where the fluid is incompressible. But on the other side, here too, these lines also come all together at the highest temperature range. So this is going to be the limit. So this is the highest temperature, the highest pressure range. Highest temperature, the highest pressure range. This is going to be the limit for the ideal gas, and you'll see the specific heats converge. And this is the limit for the incompressible fluid, and you see the specific heats also converge for all the different pressures. What I'm saying here is that here, the specific heat is no longer a function of pressure, which was the statement I made on the previous graph. I'm justifying here on the basis of experimental diagrams. Well, let's go now in the limit, the extreme limit, where these lines are vertical, and the fluid is genuinely incompressible. So that means that the specific volume, which in general is a function of temperature and pressure, is actually only a function of temperature. Well, if it's here only a function of temperature, the temperature is the thing that's different between this curve and that curve, then we don't need to look up in a table here with temperature and pressure. We just need to look at temperature. And since the line is a vertical, we can just look at the value in the saturated region. So when you're looking at an incompressible fluid for a specific volume, you can take the one at the saturation temperature here. The same with the internal energy. It is the one at the saturation temperature. Now, the enthalpy is a little different. Because the enthalpy is specifically a function of the internal energy and the pressure times the volume. So you could, at first sight, say, well, this is the internal energy at the saturation, on the saturation curve at the temperature at which you are, and the specific volume, but you keep a pressure dependence here. So that's fine. You can do that if you want to have a relatively high accuracy, and you can see that the enthalpy at a given temperature and pressure is the enthalpy at the saturation temperature plus the specific volume at the saturation pressure minus the actual pressure minus the saturation pressure. So this is a linear correction term that takes into account this second term, small variation with compressibility of the enthalpy. Note that the internal energy is not that variable. It's here, but the enthalpy is slightly variable with the compressibility of the system. So most of the time we will ignore even this correction factor. Most of the time we will just say, okay, well, the enthalpy in the incompressible state, in the liquid state or the solid state at temperature, is only a function of pressure, and it is therefore the value of the enthalpy at the saturation temperature. But that's not always the case. We will go in chapter 8, we will see one case where we have to use this formula, we cannot use that formula. Most of the time, though, if you don't go to ridiculously high pressures, you can use this formula. Now, and we will make it clear when you have to use that. So by default, you can use this, and when you have to use that in a particular type of problem, I will tell you. Okay, so now let's apply this to the definition of the specific heat under constant volume and under constant pressure. We saw specific heat under constant volume is the internal energy, the derivative, partial derivative of the internal energy with temperature at constant volume. But in the saturated liquid regime, you see that the volume is not in here at all. This is a function of only temperature. Therefore, this partial derivative becomes the exact derivative of the internal energy with pressure, with temperature. If we do the same with the enthalpy, then we can take the derivative of the enthalpy at constant pressure. So you would, to the very first term, if you use this formula, you would say, well, that is going to be the same as internal energy over temperature, and therefore Cp is equal to Cv in incompressible fluids. You can make a little correction for the derivative of this one, and there will be, in more sophisticated books, there will be a correction for Cp into Cv in solids and liquids. But for this level, we're going to say that for incompressible liquids and solids, Cp is Cv because both turn out to be the exact derivative of internal energy with temperature. Therefore, in incompressible fluids, we will assume that K is 1. And we can extend that. So let's go back to the incompressible fluid, H, T, and P, which is U, which is really only T, and then a correction factor for P times V. So du is simply, and well, let's assume also that C is Cp is Cv. We just showed that these two are the same. Let's call it C. Then du is the integral between T1 and T2 of C at T dt. dH, on the other hand, is H2 minus H1, so it's U2 minus U1 plus V, which is this V, times P2 minus P1. And so dH is the integral of C of T dt. This is du plus the specific volume times the difference in pressure. So that's a formula, that's a simplified formula that we can also use. I encourage you to look at how these formulas are derived, because it's easier to remember just a few fundamentals and then derive these than to try to remember each of these specific cases. Next lecture, we'll go into ideal gases. I'm running out of time for this reading, so I will skip this for next time and get to a summary of what we had so far. First of all, if you're going to estimate the thermodynamic property of a state, you need, in general, two variables. For simple compressible systems that are here, we have the incompressible state, well, so compressible, incompressible. We have the incompressible state here, liquid and solids. We go through the two-phase regime, and then we go into the supersaturated or superheated vapor regime. So this is a compressed liquid or undercooled liquid, subcooled liquid, saturated liquid line, saturated vapor line. Under the two, there is the dome, and here the superheated or supersaturated vapor. You can do exactly the same in the TV diagram. Subcooled liquid at certain pressures. You have here the two-phase regime, and here you have the superheated vapor. In a saturated system, when you know you're on one of these lines, you need only one intensive variable. Because, in fact, you sort of know that x is 0 here and x is 1 here. So that counts as your second variable. If you're in the two-phase regime, because you know that P and T are interdependent, You need to have two variables still, so you can use either P or T, and you can use either V or X. But you have to have P and X, or T and X, or P and V, and T and V to find where your state is. And then we just went today through the limiting case where we had the incompressible liquid on this side, where U, so if you want U in this case, you just take the U here at the same temperature. If you want H in this case, well, you just take H here at the same temperature. And if you're super picky, you can correct for that H by adding the specific volume at that point and then the pressure difference. Most of the time you don't have to do that, but there will be cases, and I will tell you when they are, where you have to do that. And that's enough for today. Thank you.